So this video will cover chapter 7. So first off, section 7.1, which deals with inverse functions. So you've probably seen inverse functions before. So if I had y equals 2 to the 2x, and I said, well, write the inverse. Well, we said the first thing you did is you flip-flop the x and y, so x is equal to 2y. And then we solve this for y, divided by 2. And so we had x over 2 was equal to y. So in terms of function implementation, we had f of x was equal to 2x. And then in terms of notation, we would have that the inverse, f inverse, is x over 2. So we have our inverse. So finally then, the way to write the inverse. So to write the inverse, we flip-flop the x and y. And so what that does then, if I think about f of x, and then I think about my inverse, and so we have here in terms of the domain, and then the range, and then my inverse, we have our domain, and the range. And so the way those work is the domain of f of x becomes the range of the inverse, and the range of f of x becomes the domain of the inverse. So inverses and how they work. All right. Well, in terms of functions then, we can talk about a function is one-to-one if for every x you only have one y, and for every y only one x. Okay. This is what makes it. So if you think in terms of a couple of graphs, so if I first draw this graph, so something like this looks like a sine wave. Well, it is a function because it does pass the vertical line test, but it is not one-to-one, and it does not pass the horizontal line test. But then if I look in terms of this graph, so my good old cubic function, looking like that, well, this function is one-to-one. It passes the horizontal line test. So inverses then. So the inverse of f of x is x, and f of f inverse of y is going to be y. So let's look in terms of a question then. So find the inverse. So f of x equals x squared minus 1, which is the same thing as y equals x squared minus 1, which means when I write the inverse, x is going to equal y squared minus 1. We bring the 1 over. So x plus 1 equals y squared. And then we take our square root. And we have that. Now, of course, x squared minus 1, if you remember, that's my parabola. And it has that U shape. And that would not pass my horizontal line test. But if we limit ourselves and say, oh, we're only going to look at it, so only has an inverse if we restrict the domain. And so I can look at either this part of the curve or this part of the curve. So then it would be 1 to 1. Okay. So the graph of the function and its inverse will be symmetrical to the line y equals x. And so a quick example of that, you think back in terms of your basic exponential graph, which look like this. My log graph, which look like that. And then my y equals x line is the line going through here like that. And so the blue curve and the red curve are symmetrical about that line. So the derivative of the inverse function f inverse of y naught is going to be 1 over the inverse of x naught, where y naught is equal to f of x naught. Okay. So that is 7.1, which deals with inverses. Right? So now we're on to 7.2, natural logarithmic and exponential functions. So y equals b to the x, and x equals log base b of y. And again, this is a little familiar. It's really the exponential form and the log form. And so ln x is the integral 1 to x of 1 over t dt. And then the derivative of ln is 1 over x, and x has to be greater than 0. Remember, logarithms have to be numbers that are greater than 0. Oh, let's see. Other things you've probably seen before in terms of logarithms are these various rules. So you had the product rule, which was the natural log of x times y is equal to the natural log of x plus the natural log of y of y. And then you had the quotient rule, which said the natural log of x over y was equal to the natural log of x minus the natural log of y. And then you had the power rule, which was the natural log of x raised to the p was p times the natural log of x. So if I had then, for example, y equals the natural log of 4x, and so dy dx is going to equal 1 over 4x and the derivative of 4x, which is 4. So this will give me 4 over 4x, which would become 1 over x. So let's look at another example. So now I want to integrate 0 to 4 x over x squared plus 9. And so here we're going to let u equal x squared plus 9. And so du is going to be 2x dx. And so now I can rewrite this. It is going to be 1/2 0 to 4 du over u, which will be 1/2 the natural log of u evaluated from 0 to 4. And so this will be 1/2 the natural log of 4 squared plus 9 minus the natural log of 0 squared plus 9. So 1/2 the natural log of 25 minus the natural log of 9, which will be 1/2 the natural log of 25 over 9, which will be the natural log of 25 over 9 to the 1/2 power, which finally becomes the natural log of 5 over 3. So inverses. So e to the x and ln x are inverses. And as you've seen before, if I integrate e to the x, we end up with e to the x plus c. Right? And if you're going to integrate e to the ax dx, you get 1 over a e ax plus c. Right? So let's look at an equation then. So let's say we now have this. I want to find the equation of the tangent line. And so we had y equals 2x minus e to the x over 2, and we have the point 0 minus 1/2. So my derivative, y prime, is going to be, oh, that will be 2 minus 1/2 e to the x. And now we can use that point to get the slope at that point. And so this is going to be 2 minus 1/2 e to the 0. E to the 0 is 1, so 2 minus 1/2 is going to give us 3/2. So there's my slope. And so we have y. And now we have our point, which was 0 minus 1/2. So y minus a minus 1/2 equals 3/2 x minus 0. Y plus 1/2 equals 3/2 x. And we can take the 1/2 to the other side. And we end up with our equation. So y equals 3/2 x minus 1/2. And we have our equation. All right, let's go through an example of another problem. So now we want to find the length of the curve. And so we got y equals 2 e to the x 1/8 e to the minus x. And then our formula is for the length is L equals the integral a to b square root of 1 plus the derivative, this thing, squared. Right? So that's our formula we're going to use. So let's do this. So first off, we need our derivative. So y prime is going to be 2 e to the x minus 1/8 e to the minus x. So that's that part. So we know our derivative. And now to use my formula for my length of the curve, I need to know what is the derivative squared. So 2 e to the x minus 1/8 e to the minus x times 2 e to the x minus 1/8 e minus x. So if I multiply that out and you do your FOIL method, you will end up with this 4 e to the 2x minus 1/2 plus 1 over 64 e to the minus 2x. And that'll be my derivative squared. So now we can use our formula. And so now we have that L is going to be the integral 0 to the natural log of 2, 1 plus 4 e to the 2x minus 1/2, 1 over 64 e to the minus 2x. Okay. And let's see, we can do a little simplifying here. 0 to the 2, square root. This will be 4 e to the 2x plus 1/2 plus 1 over 64 e to the minus 2x. Now it ends up that that thing underneath my radical can be factored. It is factorable. And when we factor this, we'll end up with 2 e to the x plus 1 over 8 e to the minus 2x, this thing squared. Square root of that. And of course, if you have a number squared and you take the square root of that, you're just left with what is inside. So we have that. Okay. And then we can integrate this. And so we'll end up with 2e to the x, 1/8 e minus 2x, evaluated from 0 to ln 2. And now it would be a matter of plugging in the numbers. So this is going to be 2e ln 2 plus 1/8 e to the minus 2 ln 2 minus 2e to the 0 and 1/8 e to the minus 2 times 0. And you number crunch that all out, and you end up at 33/16. Again, remember e and ln would cancel each other out and leave you, in this case, with that 2, right? For that. So remember your rules about e and ln, they cancel, right? All right. Other things they talk about in here is they now talk about what is called logarithmic differentiation. So now we have a problem that looks like this, and we want to find the derivative. So y equals x cubed minus 1 to the 4th square root 3x minus 1 over x squared plus 4. Right? Now let's first rewrite this a little bit. So this will become 3x minus 1 to the 1/2 power over x squared plus 4. Okay. And then we're going to take the natural log of both sides. So take the natural log of both sides, and we're going to apply those rules. We had product, quotient rules, and we do this. So now we're going to have the natural log of y equals 4 ln x cubed minus 1 plus 1/2 natural log 3x minus 1 minus the natural log of x squared plus 4. Okay. So I applied my rules, and so I had my product rule, actually had the power rule, and we had our quotient rule all being applied. Now we're going to take our derivative of everything. So this will become 1 over y dy dx equals 4 1 over x cubed minus 1, and the derivative of that is 3x squared plus 1/2 1 over 3x minus 1, and the derivative of that is going to be 3 minus 1 over x squared plus 4, and the derivative of that is 2x. So 1 over y dy dx, and this is going to give us a 12x squared over x cubed minus 1 plus 3 over 6x minus 2 minus 2x over x squared plus 4. Now we're not quite done, because we do want to solve for dy dx, so we're going to take the y over by multiplying. And so dy dx is going to equal 12x squared over x cubed minus 1 plus 3 over 6x minus 2 minus 2x over x squared plus 4. All of that times y. But then we're still not quite done. There's one more step. So dy dx is going to equal 12x squared x cubed minus 1, 3 over 6x minus 2. Where's my eraser? There we go. Eraser. Get rid of that. All right. Minus 2x over x squared plus 4. And then we can substitute in what our y was. And once we do that, now we are done. We have our derivative. All right. Next section is section 7.3. And so if y equals b to the x, then dy dx equals b to the x natural log of b. So if I had y equals 108 times 2 to t to the 12th, and I want to know the derivative, y prime, well, this is going to be 108 2 to the t over 12 natural log of 2, and then of course the derivative of t over 12 is going to be 1/12. So we end up with 9 natural log of 2 raised to the t over 12. And if we integrate b to the x dx, we end up with the 1 natural log of b times b to the x plus c. Let's see, other rules you've seen before is your power rule for derivatives. So if y was equal to x raised to the p, then dy dx was given by px to the p minus 1. Well, then if we have functions in this form, so functions in the form of f of x equals g of x raised to the h of x, then this is equal to e to h of x ln g of x. Right? So for example, if f of x equals x to the sine of x, well then we can rewrite that is going to be e to the sine of x natural log of x. And so now if I wanted to take my derivative of this, well, this is my product rule. Right. And so we're going to end up with e to the sine of x ln x times cosine x ln of x plus sine x over x. Right? So that's my rule. When I get done, I can do a little factoring. I end up with that part. Right? Okay. Oh, let's see. We had y equals log base b of x. Then the derivative is going to be 1 over x natural log of b. And so if I had a question in this form, so y equals 4 log base 3 of x squared minus 1. And I want the derivative. So my derivative is going to be 4 up front, 1 over ln 3 x squared minus 1, and then the other root of x squared minus 1 is going to be 2x. And so we're going to end up with 8x over the natural log of 3 times x squared minus 1. And that's basically 7.3. Right. So now we're up to 7.4. So this deals with exponential models. So you think about exponential growth, y sub t equals ce to the kt. And so my derivative is going to be k ce to the kt. Okay. So for example, if s of t equals 1500 e to the 0.01 t, then s prime is going to be 0.01 times 1500 e to the 0.01 t. And so this will give us 15 e to the 0.01 t. Right? So then you learn back when you talk about exponential growth, you in terms of a thing called doubling time. So time to double, t2, is given by the natural log of 2 divided by k. So the doubling time is the natural log of 2 divided by the rate of growth. Right. Other things they show in this section, they give you this formula for total energy used is given by the integral a to b derivative of et times dt, which is the integral a to b of the power dt. So they give you that one, right? And then they also talk about exponential decay. Formula is basically the same, except for now the k is negative. And so my derivative is now going to be minus k, y naught, e to the minus kt. So y naught is your initial amount, yt is your amount at time t. Right? And so then the half-life is going to be t1/2 equals the natural log of 2 divided by k. Right. So that we get up to 7.5 and the inverse trig functions. So I'm going to reference the HTML version of the book for the first part of this, because I don't want to write down all these things here, so I want to just refer to this page. So this is page 472 in the book. So let me pull this up. And so here's page 472, and down here I have, actually not 472. Where's it? There it is. There's my 472. There's 472. And there's my derivatives of my inverse trig functions given in that table. Right? And so you'll find those there. Okay? All right. So let's look in terms of using those with a problem. So let's go back here. And so now let's say we're given that f of x equals x tan inverse of x over 2. Okay. So if I look at this, this is going to be my prodigal. So let's break it out into the pieces. So this is x. This is tan inverse x over 2. Derivative of x is 1. The derivative of this inverse tangent is going to be 1 over 1 plus x over 2 squared times 1/2. Oops, sorry. And 1/2 shouldn't be there. Let me fix that a bit. And my 1/2 should actually be up here. Okay. And this will simplify to 1 over 1 plus x squared over 4. And the 1/2. Okay. When I do this out. Okay. So now I can plug it into my whole prodigal here. So this is going to be 1/2 x 1 over 1 plus x squared over 4 plus inverse tangent of x over 2. Okay. We can also have integrals involving inverse trig functions. Integrals with inverse trig functions. Inverse trig functions. And these are given on page 474. So let's go to that page. So we want to go up a couple pages. And so here's my integrals involving inverse trig functions that are given. And so let's look at an example problem dealing with that. So let's say we want to integrate 4 over square root of 9 squared minus x squared, okay, dx. So we're going to let a equal 3. And so this will be, well, you can take the 4 out front, 1 over the square root of 3 squared minus x squared dx, okay, which matches one of those forms we just had on that previous page. And so it would be 4 inverse sine of x over 3 plus c. Okay. Oh, let's see. So 7.6. deals with the growth rate of functions. And so you get this. So if the limit as x goes to infinity of f of x equals the limit goes to infinity of g of x, which equals to infinity. Right? And then f grows faster than g as x goes to infinity if the limit of g of x over f of x is equal to 0, or equivalently, E-Q-U-I-V-A-L, equivalently if the limit as x goes to infinity of f of x over g of x is equal to infinity. But there's, and then the functions f and g have comparable growth rates if the limit as x goes to infinity of f of x over g of x is given to be some number m, where m is in between 0 and infinity. So in terms of my growth rates of functions, we have this. So let f be much, much smaller than g, which means that g grows faster as x goes to infinity. And we have, and we'll see, we have real numbers P, Q, R, and S and B are greater than 1. Right? So the natural log of Qx is much, much smaller than x to the P, which is much smaller than x to the P, ln R, x to the P plus s, b to the x, and smaller than x to the x. Right. So growth rate of functions. Right. And so that gets us to the last section, which is 7.7, which deals with hyperbolic functions. And again, I'll be referring to a few pages in the book for some of the tables that deal with this stuff, right? So first off, let's go to page 487. So we're going to look at these pages. Let me just put them here. So you have page 487 and page 488 first. Right. Alright, So on page 487. So page 487. So here's my definition of my hyperbolic functions. So hyperbolic cosine is e to the x plus e to the minus x over 2. Hyperbolic sine, e to the x minus e to the minus x over 2. And then you have the other hyperbolic functions there, written out. And they're all eventually rewritten in terms of e to the x. Right? So those are my hyperbolic functions. Right? Right? And you had before, when we had trig functions, we had trig identities. And so we have here for our hyperbolic functions, we have hyperbolic identities. So just like you had for your trig functions, we have the same thing here for these guys. Right? Well, we also then have on page 489, we have this table which deals with the derivatives and the integrals of my functions. Right? Right? So we have that table. So we have these tables, and again, rather than me writing them all out, we're just going to refer to them here in the video. So let me go back to my notebook here. So we want 487, 488, and we wanted 489. Now we reference here. So if I had y equals hyperbolic secant of 3x, and so y prime is then going to be a minus 3 hyperbolic secant of 3x hyperbolic tangent of 3x. And again, that was based on that table that we referred to just a moment ago for those. Mm-hmm. So let's look at another problem. So let's say now we want to integrate hyperbolic cosecant squared square root x over. Okay. So we're going to let u equal the square root of x. And so then du is going to be 1/2 x to the minus 1/2. So this becomes 2 integral of u over u du. And so if we integrate this, we end up with 2 hyperbolic cotangent of u plus c. So 2 hyperbolic cotangent of the square root of x plus c. Let's see, another few more pages to reference here. And so we're going to look at pages 491, 494, and 495. Again, more tables of stuff. So let's quickly look at those few pages. So we want 491. So we just got to go a couple pages. So we'll just do it this way. So 491, we have this theorem 716, integrals of my hyperbolic functions. So we have this table of information. Right? We then also have on page, where am I at? Page am I on? Sorry, 491. Yep, okay. And then we want 494. So 494, we have this, derivatives of the inverse hyperbolic functions. Okay. And then on 495, we have the integrals of those functions. So we have those listed up. Right? And so let's look at an example of one of those. And so last part of this video, So one last example. So we now have this one. 9 to 25 dx over the square root of x 4 minus x. And again, we'll let u equal the square root of x, and du equals dx over 2 square root x, right? So now we're going to rewrite our integral. So now this is going to become 2 outside. This is going to be du over 4 minus u squared. And now what I'm integrating from, because u is now the square root of x, well, the square root of 9 is 3, and the square root of 25 is 5. Okay. Now we can say let a be equal to 2. And so now this will become 2, 3 to 5 du over 2 squared minus u squared. And so this is in the form of this, which is 1 over a inverse hyperbolic cotangent of x over a. And so this will become, when I do this, get the of 5 over 2 minus cotangent inverse of 3 over 2. And then again, based on those things we saw in the previous pages, this will become, I can rewrite this in terms of the tangent function. So 1 over 5 over 2 minus 1 over 3/2, which will be in hyperbolic inverse tangent of 2/5 minus of 2/3. Right? And then based on that table we had before, we said that hyperbolic tangent is given by e to the x minus e to the minus x over e to the x plus e to the minus x. So if you start number crunching that out using that formula, you should end up that the answer here is going to be on the order of negative 0.38107 for that, right? And that will conclude this video.